Okay, so today we'll talk about two-view geometry. We'll talk about relative pose of two cameras, and we'll talk about the people constraints. For the uncalibrated case, we will define the fundamental metrics. We will also talk about the 8-point algorithm to estimate the fundamental metrics. And in the end, we will talk about deep fundamental metrics estimation, which is a nice paper to estimate the fundamental metrics using deep learning. Okay, so just to remind you things that we talked about in the last classes, and to put today's content in the context of previous lectures, we talked about triangulation, where we know the camera parameters and we have point correspondences, and then we can send rays from camera centers through point correspondences and intersect the rays to get 3D points. So basically, in this case, we know point correspondences, we know the cameras, but we don't know the 3D points and their depth. So in this case, we have a linear formulation for our unknowns in the case of triangulation. We also talked about camera resectioning, where we're given an image and we don't know the camera parameters, but we have 2D 3D correspondences from the image to some estimated 3D model. And then by using these 2D 3D correspondences, we can align the camera to the 3D scene such that the 3D points are projected to the 2D point that we have. So in this case, we know the 2D points, we know the 3D points, and we need to find the cameras. So again, at least for the uncalibrated case, we get a linear solution for this problem. But today we define the following problem, which is called a two-view structure for motion, where we are given a set of point correspondences between two images. And we need to compute both the 3D points and the camera parameters. Okay, this is called structure for motion. We need to compute a structure, which is a 3D points set, and the motion, which the camera parameter set. And its formal formulation is that given two sets of corresponding point, xi and xi bar, we need to compute the camera matrices P1 and P2 and set of 3D points such that if we project the 3D points that we estimated using the cameras that we estimated, we get the projections are our input 2D points. Okay, so here's an example of point correspondence, xi and xi bar, and we need to compute both the 3D point and the two cameras such that the 3D point is projected to our observed 2D point correspondences. Now, in this case, the problem is not linear at all because we need to compute both P2 and P1 and xi. So it's not easy problem to solve anymore if we just try to solve it in this way. However, today we will see that we can use an object called fundamental metrics to get a closed form for this problem. Okay. So as before, we already talked about ambiguities, but let's define them in the context of two-view structure for motion. So suppose that we have some solution to our problem, P1, P2, and the set of xi's. Then we can use any invertible matrix H and just put between P1 to xi and between P2 and xi H inverse, which is an identity matrix, and not change the solution at all. So this equation is still correct, but we get a new solution for the problem that we denote by tilde, such that pi tilde equals pi h and xi tilde equals h inverse xi. So this can be a complete different reconstruction. It can actually distort the scene a lot, and we already saw some examples in the previous lectures for such a distortion. But we can simplify our problem using this ambiguity. So if we have some solution, P1 and P2, where A1 and A2 are invertible 3 by 3 matrices, and T1 and T2 are vectors in R3, then we can apply the following transformation on the solution. And then when we apply this transformation on P1, we get P1 times H. We multiply P1 by H. So it's this is P1. We have H here. And if we do this multiplication, we get A1 inverse plus T1 times 0. So we get just identity here, and A1 times minus A1 inverse is identity times T1, we get minus T1 from this multiplication, plus T1, so we get minus T1 plus T1, so we get 0 here. Okay, and we will get some new parameterization for P2, but the important thing here is that we change our solution to this formulation that P1 has this simple simplified form of I0, and we will be able to use it in our calculations. Okay, now let's define the epipolar geometry. Suppose that we are given a 2D point in, sorry?
In the previous slide, you just assumed that the camera 1 is located in the origin in the world coordinates?
Yes, and pointed to the z direction.
Mm-hmm. Okay.
Cool. Okay, so let's define the epipolar geometry. We are given a 2D point in one image. So we know that this point can be projected from some 3D point on this 3D red array. But for each different 3D point, the projection on the second image will be in a different 2D point. But all these possible 2D points are on one line, which is called an epipolar line. So basically, it's the projection of the 3D line that passes through P1 camera, the center of camera 1 and the pixel, and going to the 3D world, the projection of this 3D line is the epipolar line. So basically, the projection of this 3D line passes through the projection of the camera center C1 to image 2, and on the projection of any possible corresponding points, any possible 3D point to its possible corresponding point in image 2. Let's see a real example for epipolar lines. So here we see two images, image 1 and image 2. And in image 2, we see also camera 1. Okay, this camera captured image 1 on the left. Okay, and we also see some point correspondences. For example, this point corresponds to this point, and this corner corresponds to this corner, and so on. And then we just plot the corresponding epipolar lines to the point that we see here. So let's see them. So you can see all the corresponding epipolar lines. The corresponding epipolar line to this point is this line. It passes through the corresponding point and also through the projection of camera 1, of the center of camera 1. Okay, and this is true for all the point correspondences. The corresponding epipolar line passes passes through the corresponding point and through the projection of camera, the center of camera 1.
How did you know how to draw these lines? I mean, you have your point correspondence, and
so suppose that someone give me a way to compute the corresponding epipolar line. We will see soon ways to compute the epipolar lines, but now I'll just show you the ground truth corresponding epipolar lines. Okay, so the projection of camera center 2 to image 1 is called epipole 1, and the projection of camera center 1 to image 2 is called epipole 2. Okay, and all the corresponding epipolar lines, all the epipolar lines in one image pass through the epipole point, as we saw in the example. And usually, not like the example, the epipole points are not in the image. They're usually outside of the image, but it's still possible to calculate the epipolar geometry for any two views with a shared view, and also to define the epipole point will be the intersection of all the corresponding epipolar lines. Okay, the fundamental matrix is a 3x3 matrix that can transform each point x in one image to its corresponding epipolar line in the second image by matrix multiplication. We multiply f by x and we get the corresponding epipolar line in the second image. So now we will use our simplified representation for the cameras to compute the fundamental matrix given that we know the cameras. Okay, so suppose that we have x in image 1, then we want to express the 3D line of points that will always be projected to x. And we want to model it using some factor lambda, which is the depth of this point. Can someone think of a way to model this line? Okay, because we have the simplified representation of I0, we can just express this line as lambda x1, which is a point in P3. And then if we project this point using P1, we get I times lambda x plus 0 times 1, so we get just lambda x, which is a projection to x with the depth of lambda. Okay, so x lambda is a 3D coordinate that always projected to x. Now we just need to project this 3D point parameterized by lambda to the point in image 2, which we call it x bar as a function of lambda. So we just multiply this x lambda by P2. So we have P2 times x lambda, so it's AT times x lambda, which is lambda AX plus T. Okay, any questions until now?
What is the dimension of little x here?
Sorry, can you repeat the question?
What is the dimension of the small x?
It's a point in P2, so it has 3 coordinates defined up to scale.
So it's like the vector of x of lambda is like 2 coordinates and then 1, 1.
Sorry, there is a lot of noise on your side. So it's
Sorry.
the third coordinate doesn't have to be 1 in this case, but it's still defined to the coordinate up to scale, right? It's a point in P2. So it doesn't have to keep the third coordinate to be 1, but it still defines the same point. Okay. Okay, so we got some parameterization for this corresponding point x bar.
Can I also ask a question about the previous slide?
Yes, sure.
In the first row, you wrote x of lambda equals lambda x 1. The lambda shouldn't it be outside the point, like lambda of times x1? If you want to indicate the ray?
If you just use lambda outside of this point, you just define one point, right, Keen? Because in P3 also points are defined up to scale, but I want to define a group or a set of points that represent line. So if I use lambda outside of this point, I will always define the same point.
Okay.
Right, in 3D. In 3D also point defined up to scale. So I can, in addition, I can put here any factor outside of this vector and have the same 3D point. So that's why it's multiplied by x inside the vector.
Okay, thank you.
Okay.
Yoni, little x here, it's 3 dimensions?
Yes, it's in P2, so it has the 3 dimension.
Okay.
So it can be the x coordinate, y coordinate, and 1, or the same thing multiplied by any factor. Okay, to represent point in P2. Okay, so so we have a parameterization for x bar as a function of lambda, which is the depth of the point with respect to camera 1. But we know that in P2 we can represent lines using the line equation, right? L transpose x bar equals 0. So I want to use the current parameterization of x bar in order to calculate L. Can someone think of a way to do that? How can I find line in P2? What do I need in order to find line? What defines a line?
Plane. A plane?
You
So
can find 2 points and like a cross product.
exactly. If you get 2 points on the line, you can calculate the line, right? So how can I find 2 points from this parameterization?
You have the camera center and the projection of x.
Or can take 2 different lambdas.
Yes, exactly. So I can basically what the first solution is also correct, but I think that a simpler way is just to use 2 lambdas, like lambda equals 0, then we'll get t, which is actually the epipole, we'll see later. But if I just assign 0 here, I'll get just t. And I can use 1 and get this point. So I have 2 points. So what do I do next in order to calculate L?
Cross product.
Cross product.
Yes. So I just use the cross product between these 2 points, and I get t cross product ax plus t. So now I can open this equation and get t cross product ax plus t cross product t. What is t cross product t?
0.
Yes, it's just 0. Exactly, and we get t cross product ax. Okay, so this is a line parameterization for the same line instead of point parameterization as before. Okay, now we can use the cross product metrics to change some notations, but let's first see what is the cross product metrics. We might have already defined it, but let's do it again. So the cross product y cross product x is a linear operation on x. So we try to represent it as a matrix multiplication. So for example, if we have the following 2 points, x and y, two vectors. Then the cross product is defined as follows. So we can actually isolate y entries into a 3x3 matrix. And in this case, y cross product x is just a matrix multiplication of this isolation of y entries and the vector x. So we get that y cross product y cross x equals the y cross product matrix of y multiplied by x. And the notation for this matrix is just this notation, which is called the cross product matrix. And this matrix is Q-symmetric, which means that its transpose, it's the minus of the original matrix. And also it follows that for any 3x3 Q-symmetric matrix S, there exists a vector y such that S equals a y cross product. Okay, so let's get back to what we got until now. Instead of T cross product AX, we can just write the cross product matrix of T times A times X. Okay, so we do not change anything here, but now we can define F as T cross product A. Okay, this is a 3x3 matrix, and it's actually satisfy what we want. It maps any 2D point in one image to its corresponding epipolar line in the second image. And we will next show that it equals epipole 2, but are there any questions until now? Okay. Okay, so let's show now that T equals epipole 2 up to scale. So again, we have these two cameras, and first, it's easy to see that the center of camera 1 is just 0, 0, 0, right? Because if we multiply P1 by 0, 0, 0, 1, we get I0 times 0, 0, 0, 1. So it's I times zeros plus 1 plus 0 times 1, we get 0, 0, 0. Okay, so remember that epipole 2 is a projection of the center of camera 1 to image 2. So what do we have to do next in order to calculate epipole 2? How do I project this camera center 0, 0, 0, 1 to image 2?
Multiply by the second matrix, second camera matrix.
Exactly. I just multiplied this vector by a t, and I get a times 0 plus t times 1, so I get just t.
Jenny, I have a question. So this two camera matrices every time. Since we can insert h times h inverse like in the beginning, we can always bring two camera matrices to such form that the first will be like identity and a zero column, and another will look like this, right? So we do it every time just for convenience.
Yes.
Okay.
But there is also a closed form for the fundamental matrix with a general two cameras. I just try to simplify the notation for this calculation, but there is also a more complex notation for general two cameras to calculate their fundamental matrix. Okay, so until now, we saw that if we have the following two cameras, we can calculate the fundamental matrix as the cross product matrix of epipole 2 times multiplied by the matrix A, and it follows that the corresponding epipolar line to X is, we can get it by multiply X by F. So if X bar is the corresponding point to X, we should get that X needs to be on this line meaning that x bar transpose L should be 0. And if we assign L equals fx and assign it here instead of L, we get x bar transpose fx equals 0. And it follows that f transforms points from image 1 to their corresponding epipolar lines in image 2. But but we can get this equation and just transpose it because this is a scalar. And then we can, if we apply transpose on this expression, then we get the following expression: x transpose f transpose x bar equals 0. Okay, so it simply said that f transpose transform points in image 2 to their corresponding epipolar lines in image 1. Okay, so f transpose is the fundamental matrix from the other direction, from image 2 to image 1. Okay, we also define an epipolar plane. Epipolar plane is a plane that passes through the two camera centers. Okay, you can see examples for 3 such planes. So it's actually a pencil of planes. That's its formal definition. And the intersection of this plane with the images results in 2 lines. You can see here the line as black lines. And each pair of such lines, which resulted from the intersection of a epipolar plane with the images, each pair of such 2 lines is called the corresponding epipolar lines. And geometrically, for 2 corresponding epipolar lines, any point on one line will be mapped to its corresponding epipolar line. So it can be this point or any different point, for example, x0. Every point will be matched to the corresponding epipolar line. So here you can see an example for corresponding epipolar lines. For example, this cyan line is corresponding to this line, and also this red line here. So any point correspondence from one epipolar line should be on its corresponding epipolar line, and you can see that it's true here, more or less. Okay, more properties for the fundamental matrix. It has 9 entries, and it is defined up to scale, so it reduces 1 degree of freedom. But also the determinant of f should be 0, which is something that you will show in your homework, but it's simple to show. So it has 7 degrees of freedom in total. So let's think about the following exercise. You get 2 cameras, P1 and P2. And the question is, which of the 2 points, x1 bar or x2 bar, in image 2 can correspond to x in image 1? How can I solve this question?
First of all, we have to construct the fundamental matrix, and if we construct it using, so we should not forget to transpose it, I guess.
Yeah, so basically, first, just can calculate the fundamental matrix, as you said, by T cross product A. So we get, this is T, this is A, and we get this matrix. So I have the fundamental matrix. What do I do next?
Searching on the epipolar line, which is the corresponding one?
Yes, exactly. I can just try to see if I map X to this corresponding epipolar line. I can check whether this multiplication is 0, which means that X bar is on the corresponding epipolar line. So for X1 bar, if I do this multiplication, I get 1, which is not 0. But for X2, I'll get 0. So what does it mean? Which is the right point?
X2 bar.
X2 bar, right? Because it should be 0 for corresponding point. Okay, so it doesn't mean that this is a corresponding point. It just means that it can be a corresponding point because it is on the corresponding bipolar line. Okay, so in your homework, you will have to show that the fundamental metrics, for the fundamental metrics, E2 is the null space of F transpose, it's 0 is F transpose, and the determinant of F is 0. Okay, but as we talked in the beginning of this class, actually the problem is that we are given point correspondences, but we don't know the cameras, right? So what we want to do is to try to estimate F from point correspondences. And we can do that because we have this constraint on corresponding points with respect to F. Okay, so if we have two corresponding points, X and X bar, and we know these entries, we can use this equation to constrain F. Okay, so if we just open this expression, we get an equation with 9 elements. But here, X and Y and Z are all known numbers. We know them. What we don't know here is the entries of the fundamental matrix. So we actually got a linear equation in the elements of F from this correspondence, from this point correspondence. So now if I have n correspondences, I can write all these equations in a matrix form. So basically, each correspondence from each correspondence, we get a row of A from the coefficients. So we have n rows for A, and V contains the unknowns entries of F. So it's of size 9. And so again, A is a matrix of known numbers, and V is an unknown vector. Can someone think of a way to solve this problem now?
Null space?
Yeah, so if I have 8-point correspondences, I can just extract V by the null space. And if I have more, what can I do if I want to use all of them? Sorry, can you?
SVD. You said SVD.
Yes, so we already talked about homogeneous discourse problem, which can be solved by SVD. So this is the same case here. We want to minimize the norm of AV such that V is of norm 1. So it can be solved by SVD as we saw before. So F has 9 entries, and basically we need at least 8-point correspondences in order to solve V. If we have more, we will have a least square solution. Okay.
Yoni,
Yes.
Before you said that F actually has 7 degrees of freedom, not 8. So how come the extra equation that you need, or maybe I'm missing something?
Yes, no, it's a good point. I think that it's related to this slide, and
okay, then I'll wait.
Yes, exactly, because we did not take into consideration that F has rank 2 in general. In general, if you solve this homogeneous discrete problem, we will get F which is of rank 3. Because
so then you'd have to project F on a rank 2 after you solve the first. Okay.
Exactly.
Thank you.
And also, we will show another formulation that can, we'll see it soon, another formulation that originally give us F of rank 2 from 7-point correspondences.
Okay, thank you.
Okay, so how can I project F to have a rank 2?
Again, with SVD, just to
Yeah, so
rank
SVD
approximation.
is helping us a lot. So again, we can project this matrix to be of rank 2 by just zeroing the smallest singular value and calculate F. Okay, it's actually give us the closest rank 2 fundamental matrix that in terms of Frobenius norm to R calculated F with rank 3. And geometrically, you can see that if I don't apply this, the epipolar lines do not intersect in one point. So there is no epipole in this case. Another issue is that we need normalization, as we talked before in the course, because without normalization, x coordinates can be around 1,000 pixels, but z coordinates can be just 1 if I use original points, and then we get some elements which are very large and some elements which are very small, and this will result in poor numeric computation. So also for computing the fundamental metrics, it is required to always normalize the points, as we talked in lecture 2, as Mirav talked in lecture 2. And here you can see the importance qualitatively. This is the way to show the accuracy of the fundamental metrics. You just take points from one image, map them to their corresponding epipolar lines in the second image, and if everything is correct, it should be satisfied that the epipolar line pass through their corresponding points. But in this case, you see some errors, like this line do not exactly pass through the corresponding point. It's close, but not enough. But if I use normalization, then the accuracy is improved. So without normalization and with normalization. So this is very important. And let's go over on the entire 8-point algorithm, which we discussed until now. It is needed to extract at least 8-point correspondences to normalize the coordinates, then to form this A matrix and solve it by SVD, and then form the F matrix by ensuring that its determinant is 0, and then it should be transformed back to the original coordinates. And next, it is possible to extract pair of cameras that are consistent with F, which we'll see in the next lecture, and also to compute scene points using triangulation, as you saw in the last lecture. Okay, so as I mentioned before, there is a minimal formulation that uses just 7-point correspondences. So basically, we have 7 linear equations from this constraint of x bar transpose fx equals 0. So this defines f actually up to 1 degree of freedom, because we can just choose an arbitrary scale. So if we write f in terms of this unknown, and we just write an equation, determinant of f should be 0, and we open this equation, we get a cubic equation in terms of this unknown entry. Okay, because it's a determinant of a 3x3 matrix, so we get cubic element to the power of 3. So cubic equation with one variable can have 1 or 3 real solutions. So if we get 1 solution, then we are done and we are happy. But if we get 3 solutions, how can we choose the right solution for f? Because there is only one solution, good solution. Okay, I can just use another point correspondence and see which one of the 3 solutions can map this new correspondence and then choose the right solution. Okay, so in this case, I will again need 8 points. So usually the 8-point algorithm is used to simplify calculation with projection to rank 2. But this, if I get F using this solution, I'll get it directly with rank 2 because I require this to be with determinant of 0. Okay, so this.
And which method is more accurate, like this one or the linear estimation?
It's not linear because you have to solve a cubic equation.
No, I mean this method with the determinant constraint or the previous method when we
which
first
one?
solved.
Which
one
one
is better? Yeah.
So it's not as simple, like it depends on the points that you're using. If you have only 7 points, then you will get an exact solution for the 7 points. And in the previous method, you will get exact solution for the 8 points up to the projection, which can make it not exact. Usually 7 points, it's related to the next point. Like usually you want to apply robust estimation in order to choose a minimal set of points that will give you accurate fundamental metrics. So this, Ronen will talk about it, I think 2 weeks from now, but robust estimation is a very important problem in computer vision, and robust estimation methods are getting much faster as you reduce the number of minimal points that you needed. So my answer would be that it is better to use the 7 points if you have a lot of outliers, because this way you need to sample less points for estimating the fundamental metrics. But this is related to this class, so I don't want to talk about it too much, but usually you want to use as much as minimal points as you can in order to calculate your basic model. Okay. Okay, so let's see some example. Here you see point correspondence sets for this sphinx between two images of the sphinx, and it is possible to calculate the fundamental metrics and extract the cameras and then triangulate 3D points. Although this will be only defined up to 4x4 homography, so it usually won't look like this, but you will get some structure endpoints. So if we get back to our formulation, we're looking for 2 sets. We're given a set of point correspondence sets, and we want to compute camera matrices and 3D points, such that the 3D points are projected to the corresponding 2D points that are given, which we saw that it's not an easy problem because it's not linear, but we actually got a reduced formulation that at first got rid of the 3D points and just compute the fundamental metrics from the point correspondence set with a closed form solution, which is simple to solve. And basically it directly defines the cameras. So it's a way to solve the cameras, and we already know that a linear way to solve the 3D points using triangulation. Okay, so it's just a large simplification, and that's actually the importance of the fundamental metrics. So next time we will show how to extract cameras from any fundamental metrics. Okay, are there any questions, or otherwise we can take a break of 10 minutes?
Let's take a break. You can pause the record, not stop the record, Yoni.
Yes, pause, I think. Now I'll talk about a paper from ECCV 3 years ago, published by René Raftal and Vladlen Koltun from Intel Labs. So the input in this case is a set of candidate correspondences between images, but here they have outliers, which we will show we see next. and the output is the fundamental matrix between the two views. So let's get back to the homogeneous least squares problem that we defined for the 8-point algorithm. In this case, we try to minimize some algebraic error, but we consider all the points evenly in this formulation. But sometimes, and usually, there are outliers between the inside the set of correspondences. Correspondences that are completely wrong. It's not just Gaussian noise, just wrong correspondence. Like here, you see that it matched this corner with this corner, or this point with this point. And it happens a lot where there is a repetitive structure in the scene. So outliers is a real problem in fundamental matrix estimation. So in order to deal with that, there is a way to weight correspondences in a way that wrong correspondences are weighted low by 0, and true correspondences are weighted by 1. So that's the hope, but we don't know which correspondences are wrong and which correspondences are correct. So one way to do that is iteratively with an algorithm called iteratively weighted least squares. And suppose that we have an estimation for the fundamental matrix, here it's represented by x. Then we can weight the correspondence according to its consistency with the fundamental matrix. And if it's not consistent, we weight it low. If it's consistent, we weight it with a high coefficient. And then we calculate the new estimation for the fundamental matrix. And then we reweight the points and again compute the fundamental matrix and so on. So hopefully over the time we will get more accurate fundamental matrix and more accurate weights.
Can you please go again about, over the notation? So X represents the whole fundamental matrix?
Yes.
Like it's
just this notation.
Yeah.
X is the 9 entries of the fundamental, this weight. And here, instead of writing it in a complete A times X notation, we separate it. It's the same thing, but we separate it to a sum over the point correspondences.
And A of P just like represents that this points. What does A of P means?
A of Pi is this row, the ith row, like this A of P1, A of P2, and A of Pn.
Okay, and on the next slide, with weights, small pi's are what exactly?
It's a notation for the correspondence, the 4 coordinates of the correspondence, like the 2 coordinates in image 1 and 2 coordinates in image 2. Or here, like all the 6 numbers that you see in this row are Pi or P1 in this case. Okay, it's just 4 numbers actually, because you don't have to store the 3rd coordinate. So Pi is just correspondence. Xj is the current estimation of the fundamental matrix, and you have a function to weight correspondence according to its agreement with the fundamental matrix. Okay, but the problem is that how to initialize the weight? If it's very not trivial to initialize the weights, and also the updates sometimes converge to a local minimum, to a wrong estimation, and then it's not converged to the correct estimation. So in general, I can say that IRLS doesn't really work for fundamental metric estimation with the trivial implementation of IRLS. But what they did is try to learn how to weight correspondence sets with deep neural networks. Okay, and the idea is that there is a network with some weights, theta, that is used to weight correspondence set. And in this notation, they're using a diagonal matrix of size n by n, such that its diagonal entry is just a square root of the weight, just the same notation as before, but with a matrix notation. And if we are given, if we know W and A, we can extract the fundamental matrix using the homogeneous least squares, or here it's actually the weighted homogeneous least squares, but it is solved in the same way. And if we extract a fundamental matrix from this process, the important thing is that the result is differentiable with respect to the theta parameters. Okay, this is a strategy. Let's see how they do that. But that's a strategy to learn the weights, and keep in mind that the output is differentiable with respect to these weights.
Okay. Can you again explain what are the minimizing here, like intuition? Why is that giving us the true weights?
Like what is written here is the same as what's written here, but with different notation of here. Just that's the squared norm of W times this A times X. Okay, the same notation as before, like when we define the problem in the 8-point algorithm. It's just we're trying to weight out a Ron correspondence set. But the notation of the diagonal matrix is just a different notation to represent the same thing, where the diagonal elements are weights that are being learned in this case.
Yoni, maybe just you can say that here we calculate the algebraic error. I mean that each row in the matrix is multiplying the unknown vector, and you take the norm, and you expect that if you don't have an outlier, this multiplication in norm will be smaller than when you have outlier. Maybe this will help too. And the idea is that the weighting matrix is going to be such that when you have outlier, you don't want to calculate it in the sum. You will get weight which is close to 0. And when you don't have an outlier, this multiplication is going to be something which is reasonable. I mean, something which is not too large. This is maybe like,
yes, because if you have
like weighted least square, maybe maybe this.
Yes, because if X is your fundamental matrix, and this term actually measures the error for a specific point correspondence. But so for good correspondences, you want to reduce the error. But for completely wrong correspondence, it's okay that if the error is large. For example, in here, this correspondence is wrong. So I don't care if the error is large. I actually want to have a model that give a large error for this correspondence because it's wrong. So I want to have large term for wrong correspondences. So in this case, I want the weight to be small.
But basically, every 8-point correspondence will be correct for some fundamental matrix, right? So every weight matrix, that every weight vector that has 8 ones and zeros in every place, in every other place, you can calculate the fundamental matrix that will give you 0 for your last term, right?
Yes, that's
even if
correct.
it's completely wrong.
Yes, that's correct, and that's why this problem is very hard, because you can always converge to a trivial solution.
And can you explain again why can't we set all the weights to 0? What will be the what will be the problem if we set all the weights to 0?
Yes, you need some regularization for the weights. That's true, but I did not write it here. But usually, if we will see that we don't have it here because the network itself learns the weights and it applies softmax as activation, so we don't need it here. But usually when you apply IRLS, you need to have some regularization for the weights.
Wait, you said that it applies softmax?
Yes, but let's see in the next slides, because it's just we will see the architecture. But you're right that you need to have regularization for this formulation for the classic IRLS algorithm. But in their case of deep fundamental matrix estimation, they don't need it, and you will see why. Okay.
Can I have a question about this?
Yes.
In the last lecture, we talked about taking out the outliers with ransack. Can't we use ransack here to add something to the weights or get another aspect
Yes,
for the
there is
weights?
a way to initialize the IRLS with ransack, and also to just use ransack, and they compare to ransack actually, and the results.
Okay.
So
Thanks.
yes, we will see this comparison. But the standard, if you just give me this problem, I would have said use ransack to solve it. That's true. But they try to see if you can actually learn something, and it's actually, for some cases, it does better than ransack. But we'll talk about ransack in more details in 2 weeks from now. So let's not get into more details about ransack. Okay, the important thing is that this weight vector is learnable, because if you have a differentiable function that calculates these weights, you can derivate this SVD process. There are 2 SVDs here. One to calculate the homogeneous least square solution, and one to project the F to rank 2. Both of them are differentiable, and you can use learning algorithm to optimize your functions that estimate the weights. Okay, so they have 2 neural networks. One of them is called WINIT. So it just gets, there is no any initialization here, it just gets point correspondences. So we have n point correspondences, each one represented by 4 numbers, the XY coordinate in one image, and the XY coordinate in the second image. And we have n correspondences. And possibly you can also add some side information for each correspondence. For example, the score, the matching score of the points from the method that used to calculate the point correspondences, like the SIFT score for the correspondences. And the output is a set of n weights, a weight for each correspondence. Okay, that's the high-level architecture.
Can you explain again what is side information?
And they just gave an example for the score of the matching point. Let's say that you have feature for each point. How did you decide that these points are corresponding points? You have some feature and you calculate the distance between these 2 features, and then the side information can be this distance, or this over the probability that these points are real corresponding points. But you can use different things. They just use the score of the correspondences. Okay, and they have another neural network which it's called a WITER that update the current weights. Okay, so it's again get the correspondences, the side info. They have the previously the previous outputs of weights, and they have the residuals of the current correspondences with respect to the current estimation. It's actually the error of each point correspondence, the current error.
The residuals are the
We
deviation
define them
from
in the next
from.
slide.
Okay, sorry.
Yes, it's just the symmetric equipolar distance error. So you take one point from one image, map it to its corresponding line, equipolar line in the second image using the currently estimated f, and you measure this distance. So if f is completely accurate with the point, you will get a 0 distance, right? So they do it symmetrically. This is a known term in fundamental matrix estimation. So we get two terms and we sum them to get the residual of this point correspondence with respect to the current estimated f.
Jenny, so these distances are just like that matrix A times the current fundamental matrix, right? The row of the matrix A, which is...
No, so actually not exactly. They use the geometric distance. What you say is the algebraic distance. They measured actually distance from point to line. It's not the same. It's not exactly the algebraic weight. If you look at these terms, this is algebraic number, the absolute value of this term, but you define it by these terms in order to make it something with geometrical meaning and not just an algebraic number. You just measure the distance from the point to the line. Okay, that's visible. It's a better metric for residuals, which are harder to optimize, but you can measure it. Okay, it's just that's the definition for the residual. It has a geometrical meaning, which is better than the algebraic meaning, which is only the dot product, as we said. Okay, so their forward pass uses a forward passage from W init and W iter. First, we construct A using the point correspondences. Large P is the set of point correspondences. We use W init on the point correspondences and side information to get the initial weights. Then, using the weights, we solve the homogeneous least squares problem using SVD. We get the current estimation for X. Then we calculate X is just a vector of 9 elements. G of X is a fundamental matrix of rank 2. Okay, it's just the SVD projection to rank 2. So once we have the fundamental matrix, we can construct the residuals vector. And then using PS, the point correspondence, the side information, the current residual, and the previous weights, we compute the next weights. Okay, so iteratively we update the weights, capital D times, and then we get the fundamental matrix. So all of what I described now is just a forward path to estimate fundamental metrics from point correspondences, and then they apply loss to train both W init and W iter.
So what is the loss to minimize the
Yes,
residuals?
we will see soon. Just before the loss, I want to say something important. In this problem, the order is meaningless. Like the order of the endpoints is just arbitrary order. Okay, it doesn't mean anything, not like an image where you have a real order of the pixels. Now it's just selected randomly. So it's important to make the network also equivariant order. What does it mean? If, for example, I replace, I do some permutation to the inputs, like I change n to be the first coordinate and 1 to be the last, the first correspondence, and 1 to be the last correspondence. What should I expect from the output weights? Yes, exactly. If one is an outlier, I expect that I will get 0 now here. So I want to have the same permutation on the output like I have for the input, and this is called a permutation equivariance. So they used an architecture called the point net architecture, where each correspondence goes through the same CME's linear layer. So each correspondence in each layer is applied with CME's linear layer identically. So the order is not important if you apply the same operation on each correspondence separately, and they increase the number of channels over the time. But in order to share information between the different correspondences, they use a layer called instance normalization, which basically just normalize vectors of the features between all the points with a permutation invariant operation. Okay, so they use the mean of this vector and the standard deviation of this vector, so the order is not important when you compute these functions. So again, you have a way to use the permutation equivariant architecture, but by just using identical operations and sharing the weights with permutation invariant operations. Okay, if someone is interested, you can read the PointNet paper. It's an excellent paper. But that's it's important to note that the architectures should handle these permutations correctly.
What is the Siamese? What is the Siamese?
Siamese, it means that you apply the same layer. You have n vectors of d features. So you have a matrix of like 64 by d, which you apply separately on each input, the same matrix.
Oh, okay.
They share the same weight, unlike a general fully connected layer, which can be different for each input layer. Okay, so the loss function uses the ground truth correspondences in order to give a loss for the estimated fundamental metrics after all this forward pass. So they use the same residual function that we defined before, the symmetric equipolar distance, and they bound the error by 1/2, 0.5, in order to make it robust to very bad or very hard problems. Okay, so that's their loss function, and they know the ground truth correspondences, so they want to just minimize the residual for the ground truth correspondences. So they use the ground truth. It's a supervised problem.
Jenny, can I go back to the architecture? You said that the output of the network, so the weights, we get the weights after we apply the softmax, right? But that makes the weights sum up to 1. But why we require that? You said that we want like good correspondences to have bigger weights, so like 1, and smaller weights to weight less, so like 0. Why we apply the softmax? Why we don't apply, for example, element-wise sigmoid function to make everything from 0 to 1, but we do not require the weights.
Actually, I'm not sure. It's a good question. I was wondering also why they use softmax. I think that it was just something that works for them, and it makes all the weights positive, and maybe it helped them to converge because softmax has a tendency to choose to give very high weights for some correspondences, and so it was easier to converge in this way and not fall into minimals like everything is 0 or everything is 1 using the softmax, but they did not talk about it in the paper.
Okay.
But it's a good question. I agree with you. I would have do what you said, just apply like a sigmoid on each layer, on each output.
But then they will not.
Applying sigmoid.
What?
Applying sigmoid on each output would make the trivial solution of all 0 weights possible. So maybe that's the motivation to use the softmax. It avoids the trivial solution.
It's like a regularization for the weight.
Yeah. Instead of regularizing the norm of the weights to be something. So maybe, but I don't know.
Yes, possibly. Makes sense. It's another explanation. Yes, interesting. Okay, so results. Let's see how much time we have. Okay, we have time. So they compared here. This is the number of iteratively rated updates. So what they measure here is a bit complicated. The idea is that we want to have more inliers, but we want them to be more accurate. So if we have a lot of inliers with a low error, we are happy. So as you can see, with more updates, the results got better. And also they compared the results, the times is to compute the forward pass is larger, but they get better solution. And if they use the 5-star, which means that they do not use side information, the results are less good compared to with using the side information. And they also show the baseline for direct registration, which direct regression, which means that they do not do weighting at all. They just use all the point correspondences, including the outliers, and you can see that the results are really bad in this case. So the results here are for tank and temples, which is this data set. But there are different scenarios like car driving, which is here you see the Kitty data set. And what they try to show is that if you just apply the results on Kitty, you get this is this row, you get similar results to the baseline methods like Ransack and USAC and all these classical state-of-the-art methods. You get similar results. But if you, in addition, train specifically on Kitty, it improves the results on Kitty a lot, and you get much better results compared to the state-of-the-art methods. But it's impressive that without any further training, by just training on tank and temple, they were able to get good results for Kitty compared to the state-of-the-art methods, comparable to the state-of-the-art methods. Let's see some qualitative results. So here, red are inliers, blue are outliers, and here you can see the second image with the corresponding prepolar lines. The green are the estimated lines, the blue are the ground truth lines, and you can see that they all pass through the corresponding points as required. Here is another not easy example. You need to find fundamental metrics between this image where the gate is small to this image where the gate is large. And you see that the results are close to the ground truth results. And another nice example.
Can I get back a little bit on the results? These networks don't use any visual information, right? They only use point correspondences. Then why does it matter? Like why different data sets matter? I mean, the information is basically the same. We have different point correspondences from two images, but those images can come from whatever source. And I just don't understand.
Why does it matter? Yes, I think that you see here the motion is always forward. So the pairs that you're computing, the fundamental metrics here, are for forward motion. So the fundamental metrics actually usually looks like what you see here, that you see the people in the image because the next camera is just in front of you. So you see the next camera in the image. So this is one pattern, but for tank and temple, there are patterns where camera is rotating around an object. So in this case, the people is not inside the image. It's just on the side of the image where the other photographer stands. So the prepolar lines are mostly parallel, right? Because the people is not in the image. So you get a much different pattern of mapping. Instead of mapping such that the people is inside the image, you get a mapping where the prepolar lines are parallel and you don't see the people. So here you are right that the examples that I show here are examples, most of them, the people are inside the image, which is a bit interesting, but this example is very different than the Kitty motion. It's not a forward motion, it's moving a side motion. Okay, that's why
improvement in terms of complexity using deep learning.
What? Can you repeat the question? I did not.
Is there any improvement in terms of complexity? Did they talk this about in the paper?
What do you mean by complexity?
Complexity, like ransack state, you need to compute many, in ransack you might to compute many
In terms of running time?
Yes, and runtime.
Yes, they wrote the running time for Tank and Temples, which I think that it is for one sequence, so this is very fast. With ransack, you usually will need more time, but they did not compare the running time for ransack, so I'm not sure. It's a good question. If it really saves the running time. Maybe in the papers they have such a comparison, so you can look after and see if they compare the running time between the classical methods to the deep learning method. Let's see some failure cases like here. So the people-hour lines, the ground truth people hour lines marked in blue are different than the ground truth, the estimated people-hour lines marked in green. But it's interesting that all pass close to the inliers. So maybe this solution is not constrained enough for the method to converge, although I think ransack could have handled this. Here is another similar case, where again, the fundamental matrix is wrong, but there is a good matching between point correspondences to lines. Okay, any questions about this paper? Okay, it's a good paper. You can also look at it after.
I have a small question, not about the paper, but just in general.
Okay.
If I see the intersection of the epipolar lines, it's either because the camera is in front of me or behind me, right? Even if the camera is behind me, I'll see the intersection in the image.
Yes, that's true.
Would you recommend using this or the regular previous method?
I think that they don't have code, but last time I checked. So if you want to implement it, you can use it. I've never used it, but if there was a code, I think that it might be useful to try this for your specific problem to see how it works. Again, if you have some two images which are very different than their data set, it probably won't work very well. But if you have something that views that are very common, then it might work. Like Kitty is almost always the fundamental matrix very similar between pairs of views. So Kitty is an easy example. So because the motion is similar between pairs of views, so they just I'm not surprised that by training specifically on Kitty, they improve the results very much. But it's kind of to memorize this car motion, basically. So I don't think that it can really fit your data set like it worked for Kitty. But yes, it can work. I've never tried it. Okay, so to sum up, we talked about relative pose of two cameras and the epipolar constraints. The uncalibrated case, we developed the fundamental matrix and the 8-point algorithm to estimate fundamental matrix. And we also saw some overview for the deep fundamental matrix estimation paper. And so next time we will talk about extracting cameras from F, how to do that. And we will also develop the same idea of fundamental metrics to the calibrated case. So in this case, it's called the essential metrics. But we'll see it next week. Meanwhile, you can listen to this cool song about the fundamental metrics on your free time. It's very funny. So that's it for today, unless there are more questions.
You can just stop the record, Yoni.
Yes.